Hey everybody, this is Becca. I'm from Empowering Pumps and Equipment. We are a resource for the pumps and related equipment industry. Today I have Ralph and Chelsea with us. They are from CF Turbo. So today we're going to talk about hydraulic design of multi-stage pumps. So this is going to be part one of a two-part series. And today we're going to be talking about the basic modeling and CFD simulation. So Chelsea, why don't you introduce yourself?
Hi everyone, I'm Chelsea and I'm the digital strategist here at CF Turbo.
Hi, I'm Ralph Müller. I'm co-founder of CF Turbo and currently I live in Brooklyn, New York, and I'm the president here.
Awesome. Well, thank you both for being here today. And Ralph, why don't you share your screen and we'll get started.
Okay. Okay, 1 second. Okay, Chelsea, we can start, I think.
Great. Welcome to our webinar, everyone. Like I said, I'm Chelsea. I'm the digital strategist here with CF Turbo. CF Turbo is a German-American software and engineering company specializing in turbo machinery design, software, simulation, and related engineering services. In this webinar, we are going to talk about the basics of multi-stage pump design and CFD simulation. Questions we want to cover today are, why are there multi-stage pumps? What are the basic design principles? Which types of multi-stage pumps are around and for what applications? How can a conceptual hydraulic design be done from the ground up? And what is essential to know about the 3D flow simulation of pumps? In this live demo next, we'll demonstrate the hydraulic design for a pump stage, setup, and export of a 3D CFD simulation within CF Turbo. So, why are there multi-stage pumps? There are several reasons. First, we look at a diagram of hydraulic efficiency over a specific speed. If the specific speed for a required duty point falls to a level where the efficiency would be too low and the energy cost becomes too high, multi-stage pumps become a choice. That's the case if rotational speed cannot be increased. Secondly, the operating range of pumps can be enlarged considerably by using the multi-stage concept. Whereas all stages deliver the same volume flow, the stage head arranged in series adds up to the total pump head. And third, for some applications, like borehole pumps, there are constraints for the outer diameter. With multi-stage pumps, it's possible to reach the duty point with a small radial extension. And finally, it is often necessary to limit the head per stage by using a multi-stage concept for mechanical design reasons. In a multi-stage pump, in general, the fluid flows from the outlet of one impeller to the inlet of the next. There are different ways to do that. Here we have selected 3 major design principles to distinguish multi-stage pumps. On the left, we have single entry inline configuration. In the middle, there's a single entry back-to-back design. And on the right side, we see a double entry back-to-back model. And back-to-back designs are built to minimize the axial thrust. So in the following slides, we'll show 5 different types of multi-stage pumps. Of course, there will be more concepts and variations around. Multi-stage pumps have a wide range of applications in many different industries, like water supply, energy, oil, process industry, and others. This image shows a single entry axial split casing pump. The casing is divided in 2 parts by an axial cut. It allows access to the whole rotor for replacement or repair. And these pumps are used in chemicals for water supply, as well as in the oil and power industry. Variation of the axial split casing pump would be this, the multi-stage double entry pump, as shown here. Typically 2 or 3 stage pumps of this kind are used for water transport. The fluid is distributed by a forked pipe to both suction nozzles. The double entry design concept reduces NPSHA requirements compared to single entry, and better efficiency can be achieved because no axial thrust balance device is needed. So the slightly higher design cost of a multi-stage double entry pump will be compensated quickly by running the pump 24/7 in large pumping plants. Next, we have multi-stage segmental pumps, also known as ring section pumps, which are used widely for different purposes like reverse osmosis, reactor feed, condensate return, or mine dewatering, among others. Each stage has an impeller, a diffuser, and a return channel with guide vanes. The stages are arranged between inlet and exit casing, which are braced by strong tie bolts. Here we have the barrel type high pressure pumps, which are built for extreme pressure. An assembly unit of pump stages, the so-called cartridge, which is similar to the ring section pumps we just saw in the previous slide. They are contained in a barrel. Barrel type pumps are used, for example, as boiler feed pumps in fossil fuel power plants, and similar pumps are applied for water injection duties in oil fields to boost oil extraction. And next we have vertical multi-stage radial and mixed flow pumps, sometimes called vertical turbine pumps or vertical submersible pumps. These are used for irrigation, deep wells, seawater lift, utility circulating water, industrial process pumps, fire services, and others. They have applications in the water industry, marine, power, oil and gas, as well as industrial process pumps. And now it looks like we can start our live demo. So I'll hand it over to Ralph.
Okay, thanks, Chelsea. Very nice introduction to this topic, I think. Yeah, today we want to show the design of a multi-stage pump, how it is done in CF Turbo, and I have chosen the following design point. You see here 10 cubic meters per hour, which comes to 44 gallons per minute. The head would be 20 meters or 68.9 feet. Rotational speed is 3,600 RPM, and the fluid will be water at 20 degrees Celsius. So, but before I give these live demo to design the pump in CF Turbo, I have also 3 introductory slides. So first I want to show briefly what is the design methodology of CF Turbo. And CF Turbo, you start from a design point. As I just mentioned, this is the best efficiency point in most cases, defined by flow rate, head, rotational speed, and fluid inlet conditions. And from these 5 numbers, we start our design. And in CF Turbo, we have 2 major drivers. One thing is we have these fundamental equations of energy and fluid mechanics, like the Bernoulli or Euler equation. And we have numerous empirical correlations, which give us a reasonable design in the very beginning. And these empirical correlations are public knowledge, publicly available, or you could also use your own data in CF Turbo. And the output would be then a 3D CAD file for the fluid and for the solid domains, which can be then later used for detailed CAD drawings or for CFD and FEA simulations. So, and today we want to show how we come from CF Turbo to CFD and how we use it there. And we have chosen out of many solvers which are available on the market, ANSYS and Cimerix, and we want to show one example with ANSYS and the other one with Zemerics. And besides these codes, there are also other interfaces available. Just a short word about optimization. This will not be a topic of today, but it will be a topic for the next webinar and the second part of this. So CF Turbo can be integrated in simulation workflows, and it's a pretty straightforward setup to work with simulation codes and optimizers. And you see here some of the commercial codes. But as I said, this will be more a topic for the second webinar. So, and now I'm ready to go to CF Turbo and start the simulation. Results will come later. So this is the GUI of CF Turbo. Besides pumps, we could also build fans, compressors, or turbines. Today we build a pump and we choose our pump module. And as said before, right, we put in our best efficiency point, our duty point, which is with 10 cubic meters per hour, 20 meters head, and 3,600 RPM. Fluid will be water, and at 1 bar inlet pressure and 20 degrees Celsius. I should mention here is we have a database in CF Turbo, so-called CoolProp database, and you could use this and choose fluids among these database for the design. And besides this database, you could also create your own fluids or your own mixtures. Right, on the right side we have here a sketch of the specific speed, and you would see we were on in an let's say allowable range. Specific speed is about 20, and we could build a single stage machine. However, we have for this typical application we have a limitation in the outer diameter. This is one thing what mentioned before why we built a multi-stage pumps. So this will be really an radial extension is limited to 50 millimeters. So, and that's why we want to go for multi-stage, and we have chosen this example. So, and we start with the first impeller design, right? And you come here to the main dimensions window. And the first what we have to do, because we want to build a multi-stage machine, so we know this will be a 3-stage machine from a previous estimation, and the energy fraction will be 33%, and then the head goes down. So this we designing this specific impeller for the reduced head, for the head of 1 stage, right? And in CF Turbo, always on the right side, we have here some empirical or some important informational values. From there, we go to our parameter section, and this is here where the intelligence of CF Turbo is behind it. Now we have, I talked about empirical correlations for getting the main dimensions of the impeller, like intake number, right, or work coefficient. And all these functions, what you see here, really are open. So CF Turbo is not a black box, and you can edit these functions if you want. For the outlet width ratio as well. So you could, with this empirical data, you could get a reasonable initial design. And because we have nothing else started with than with these 5 input numbers, so we also need an estimation of the efficiency of the stage efficiency, but also of the volumetric efficiency. So there are functions around which are very helpful to us. Let me think, I have to reconsider this. And now we go for the main dimensions, calculate. We see here a sketch. We recalculate this because we have changed the head. So, and I know we need a certain diameter for the shaft. It would be here 25. We recalculate our main dimensions. Yeah, the shape changes, and we see here also an idea where we are on the coordinate diagram. So, and before I proceed, I just make here straight numbers in millimeters out of it. And 8 millimeters. So, and from there on, we can go to the next design step, which will be our meridional contour. And yeah, you see here a hub and shroud contour, hub contour is blue, shroud contour green, and these contour can be managed and modified in many different ways. It's very flexible in creating the geometry. On the right side, you see cross-section area distributions, static moment or curvature, for example. And it's not only, let's say, a drag and drop, you can also edit these angles or these numbers, for example, by a certain value. Right? So besides these modifications, we could see also here our meridional flow calculation. This is based on a potential method, and we it gives us a first indication about the velocity in the impeller. And besides these values, we can build now the hub and shroud solids. I can activate this. Let me move this one. I can activate hub and shrouds, and I leave it here as a very simple shape, right? So we can edit any of these contours by splitting or also by moving the points, for example, right? Okay, secondary flow bar is not here needed yet, and I go to the next design step, which is our so-called blade property window. Yeah, we'd have to choose here the number of blades. I keep it as it proposed with 6. Number of spans, I think I can go down to 3. CF Turbo has different blade types which you can choose. This is mainly for manufacturing reason, but for pumps, I think we can stay with freeform 3D because these impellers will be casted. And the blade thickness will be on the hub and shroud, and leading and trailing edge will be an input value. And not forget to mention, we have here our slip factor correlation, and the most common is the Gülich and Wiesner correlation, where you see the function which is behind this here also on the right side. All velocity values, so the kinematics can be seen here on the right side, and we go for our blade angle calculation. And this is, we get a very reasonable approach. So when we see we have blade angles in the 20s, so this is very common, which will bring us also a decent efficiency of the impeller. Next design step is the so-called mean line design. And we have here our 3D preview in it. Very nice that you can see immediately what changes. We have a different physical values based on the Stanitz and Prine method here, from blade loading over static pressure. So many different values which are helping to design the flow channel, and we have also here a static pressure calculation on the lower side. And CF Turbo has not only these traditional MT or M theta design. Yeah, you see here on the left side in this big diagram, you see the true blade angles of the blade, and we can change here on this side the wrap angle, for example. Right, this is one of our capabilities, which changes then also, of course, the flow channel. In the end, it will have an effect also on the pressure rise and on the efficiency, right? What you do. But we have also many different or 2 more possibilities to create our blades. It would be the blade angle direct, which we can put in, or we can go over a a blade loading distribution. Yeah, this is sometimes called inverse design. I think it's a bit misleading. Yeah, it's nothing else than a certain design method to get the blades. And I go back here to the conformal mapping. Yeah, and we already now with our mean line design, which determines the curvature of the blade from the leading edge to the trailing edge, including the wrap angle, right? You see it here. Next would be blade thickness distribution. And for these types of pumps, I think we can keep this, we can keep this constant. Yeah. Again, we see here, we have here the possibility to see different physical values like the static pressure or also the tangential coordinates, and always an immediate 3D preview. It's not necessarily linear. We can also use freeform profiles, and we can read in if we want to. We could also read in profiles from a profile manager to get a certain thickness distribution. And we go back to linear here. Okay, and then we only have to define the last design step for the impeller would be the leading edge and the trailing edge, and we have here different methods from simple over elliptic, Bezier, or linear. Yeah. I prefer to work with elliptic shapes, or we could, or here, for example, for the trailing edge, yeah, we could also build, let's say, a Bezier or another one. But very often these type of impellers are left blunt in the trailing edge. So and now we have our model there. We can see it in 3D again, right? So a full 3D model. And now we are ready for the next design step, which would be our diffuser. But before this, I would save my file. I call this here stage 1. Simple. And save it. Next design step will be the bowl diffuser, and we add here we call this a new stator. And we have different possibilities also for stator design. Could be vaned or unvaned, freeform shape, radial diffusers, bowl diffuser, or we have 90 degrees bends in one or the other direction. And for this purpose, we will choose our bowl diffuser option. And basically, we can work with an extent on inlet, or we can work with inlet and outlet numbers on hub and shroud. And I would here prefer to go a certain length. Make this thing a bit longer. Oh no, this was wrong. I want to go reset this, and we want to go on the outlet. Make this just a bit longer. Okay, and then let's see on the inlet. Okay, this is the upstream model. I think we set it to default. Go to inlet and outlet. Yeah, make here our correction again, because we need a gap between the rotating and the non-rotating component, and we want to build a vane stator, so with blades. And now it's very similar. The design steps are similar to those from the impeller. Yeah. I can modify the shape here in the meridional contour after setting the main dimensions, right? So, and I have here these capabilities in moving the Bezier points. I can define my leading edge, for example, the angle. or instead of a Bezier, I could also set a straight line and reposition this, right? So, and then I have here Bezier points in where I can move the curvature of my contour, and I see an immediate effect on the meridional flow on the right side, right? And here we have our 3D option, and we could also see for our example, let's say, yeah, informational values would be helpful here in this case. So, but for an initial design, okay, we can work with this, I think. And as before, we can build your hub and shroud solids. I just activate this for a reason that we see it later. And I show you then an example which will be much more, let's say, detailed and complex. And after creating the meridional contour, oh, I have to cancel, I have to go back here. Let me think. I want to modify the hub and shroud solids that they do not overlap. And I just can do this quickly. What's this with those one? Right. So now it's a different one, and we go to the next design step, which will be our blading. Number of blades is your proposal based on pressure calculation, and then we should look that we have the right combination between the impeller and the stator blades. And I choose here 8 blades, and we go number of spans. I think for this demo I would go down to 3. The blade thickness should be a bit higher. I go for 2 millimeters before switching to the next. Right. So, and then we could modify here our, let's say, our mean line profiles, changing the wrap angle if we want, and then looking for a certain curvature and pressure distribution of our blades. Right, so, and then we see how we modify. When we modify the curvature, we see how the blade loading modifies, or we could do it vice versa if we want, right? Giving the blade loading, seeing what happens with the pressure distribution. So yeah, we see our 3D model. Could make the wrap angle a bit shorter. And now I'm able to go to the next design step, which would be the thickness distribution. I leave this constant here, and again, I would use elliptic models on the leading edge. On the trailing edge, this time I would go for Bezier type, slim trailing edges. Yeah. But to make this correctly, I have to go back to the meridional contour and set the position of my trailing edge away from the outlet of the diffuser. So, and this is here now. I can modify the position. You see here, I can modify the position of my trailing edge. And then we see the 3D model. So, and this is the basic, let's say, component of our multi-stage pump. and with a very simplified hub and shroud contour, right? And since we are limited in our time in this webinar, so from here on, so I will switch how to come to the next 3 stages by reading in already prepared stages, right? So the simplified model could be, of course, much more detailed. Yeah, we can also, or we have to also bring in a leading on the leading side, on the inflow side, we have to bring a certain inflow region, and all this is prepared now in the next model, which I will show you. So I switch here from this one, yeah, save this. I switch this one from this one to our prepared first stage. So, and you would see here the difference. You would see immediately the difference, right? So I have a more detailed hub and shroud design. I have a secondary flow path or leakages in it, and I have added also a nozzle on the inlet side. So this would be then our first stage, which is way more realistic than, let's say, the initial conceptual design. But I didn't change anything of the blading, right? So that means the hub and shroud contours and the blades remained the same. I've just added these solid parts here and the secondary flow paths. So, and from here on, I would go to add the second and the third stage, and this works like this. You can here say add new component, right? And then you see here load from CF Turbo file, and then I read in these prepared or just copied stages, and now it would be stage 2, and I check impeller and stator. And I don't want to import or override. So I want to make this active, both components. Right. And as I did this before, I read in the next from CF Turbo file. And this is, I had called this before stage 3. And it's not only an impeller and the stator, I have also added an outlet region or 2 outlet regions to prepare the computational model already in CF Turbo. This is one of the big advantages here, that we really can make detailed designs before we go to CFD without applying another CAD system. So we activate. These 4 components. Right, and then we would have our 3-stage model. So the only thing what we didn't have it activated here right now would be the secondary flow path. So this is here now in the 3D view on CF Turbo, right? And I would save as a, this is not stage now 1, 2, and 3. So and this is how we get our first full 3D model, right? What we can do here is so-called model finishings, and also then closing the gaps to build here the leakage flows. So we have to decide, do we want to have a simulation with a leakage flow or without? So in the first part of the webinar, so we talk about only the models without the leakage flow, and in the second one, then we will come up with the leakage flow. So, but for today, I think this is the model which I want to show you. And this is here our final model, which will then go to including the leakages, which will go for 3D flow simulation. Right. So I'll show you here again. You can clip this. And this is this will be our geometry for the computational model. Okay. So now we can, so what I mentioned before, we took this model, so we brought it to ANSYS and to Symerix, and I have a few slides which I want to explain the simulation results for this geometry. And please remember, we did not apply the leakage flows here for this first simulations. So, and I go back to our PowerPoint. So for the export for ANSYS works, yeah, pretty simple. It's CF Turbo is fully integrated in ANSYS Workbench, and therefore, so it's not in a way, it's not an export. It's really part of the Workbench where we prepare the model and then have the access to the meshing tools and to the solver and post-processing. And in this case, we used or we have just built a flow passage, a simplified model, right? Not the full 360, no leakages. We have applied a TurboGrid to mesh it, and in the end, it was a 1.3 million nodes mesh. All the setup, manual setup, until we could start the run was about 60 minutes. And then we made one simulation on an i9 notebook per 500 iteration steady state with SST turbulence model, and the computational time was about 75 minutes for this run. And alternatively, we ran a simulation in Symerix. So here we choose a 360-degree model because currently there are no flow passages available. Again, no leakages. It's an automated meshing tool. It's called binary tree hexa mesher. We came up with up to 4 million nodes. Meshing and setup took only 10 minutes, so we have highly automated this in CF Turbo. And then we ran a steady state and a transient simulation, both with K epsilon turbulence model. For the steady state, we used also 500 iterations, and the transient were 4 full revolutions where we, let's say, post-processed and only the last one. And computational time, 30 minutes for the steady state and about 2 hours on the for the transient one, and on the same notebook with 8 cores. And yeah, talking briefly about the results. So what we have here, so you see a post-processing screenshot from Symerix. So we have immediately reached an excellent impeller efficiency of 92%. We met the targets of the required head of the pump, the total head. And but what we had to observe, so you see here in the diffuser, there are some separation areas, and this would be a matter of modification later, right? So, and to compare this data with ANSYS, very similar. So here we have some blade-to-blade views out of ANSYS, and I have prepared a little table. You see here the required head, 20 meters is reached or nearly reached. And you see the different head in the stages. And again, these excellent impeller efficiency. And then we have these drop into the stage efficiency, and we could determine the reason this would be the separation. And in our next webinar, then we will talk about how to improve these design, right? So, and generally speaking, yeah, we reached our target. We have good agreement between the results between ANSYS and Semerics, but also the results for between steady state and transient. What we did from Semerics had a good agreement, but this should be for a, let's say, for a best efficiency point design. Is this not unusual? What's also not unusual is a certain drop of head and efficiency in the second and third stage compared to the first stage of the pump. And so this is a thing which has to do with the inlet flow conditions of the, let's say, of the stages of the second and the third stage. Right, and I could, yeah, to see here to give you an impression that how it looks in our CFD codes. So this is the environment in GUI of Semerics. You see here some streamlines, and all is, let's say, it's showed with pressure. And on the low side, we can see besides residuals, we see how the head evolves over the iterations, or the efficiency, or for example, the shaft power. And we have here this phenomenon that we see. We have these excellent impeller flow, and we have these separation areas in the diffuser. And the same we could also observe in ANSYS. So we have these, yeah, I have here streamlines colored by velocity, magnitude velocity, and you see here first, third, and second stage, and a very similar behavior in these three stages, and our, let's say, impeller and diffuser comparison with these little separation area. And this will become interesting, how to improve the efficiency and the head then in the next design steps. So, but for today, we are basically done, right? So we have a reasonable initial design, and overall, when we see it, yeah, we made a design in let's say half an hour, and then a simulation which took us, depends on the method, 1 or 2 hours. So within a reasonable time, we got a reasonable design, and from there on, we want to go to the next steps. So this will be a simulation with leakages. We want to run, make this big here. We want to run performance curves. Then there would be, of course, the topic of stage optimization, especially looking at the diffuser. But we could also think about, let's say, improving the NPSH behavior of the first stage. Sometimes in multi-stage pumps, the first stage is different than all the other stages. So this could be a topic, and we will talk the next time about optimization. So what would be a possibility to optimize the geometry, to improve the geometry, and we want to compare a sort of manual interactive optimization done by experts compared to an automated optimization by mathematical algorithms. And that's from my side. And yeah, I'm looking forward for the second part of our webinar, but we are ready for questions.
Thank you very much, Ralph. Let us get back to our regular screen. If you're going to stop sharing.
1 second.
All right. Thank you so much. That was awesome. So I do have some questions for you. So the first one is, for you, Ralph. So how many stages can be designed in CF Turbo in one session?
Yeah, currently it's with the release 2020 or 2, we are with 5 stages, and we will increase these numbers step by step with current releases. Right? I know there are other types of turbo machines which have much higher number of stages and which also should be computed as a whole. So, and that's why we continue increasing the number.
Gotcha. So since you said other types, what type of turbo machinery can be designed with CF Turbo besides pumps?
Yeah. Besides pumps, yeah, we can do many types of axial, radial, and mixed flow pumps, and also blowers, fans, compressors, and turbines. Right. So we do not cover yet all the scope, but for example, this is also a matter of continuous development, that we add step by step more modules to cover all turbo machinery one day.
Absolutely. And yeah, it does take time to be able to do all of that, but you're definitely, able to help people with a lot of different designs. So that's great. What determines the stage number limit?
Yeah, okay, that's a very technical question. So it's mainly limited by vibration problems, right? So I think the critical speed goes down, and then you have to. So there is a limit in the end what you could add together in depending on the shaft and on the mechanical design. Not from the hydraulic, from the fluid mechanics side, there would be no limit. It's mechanical driven. Okay.
Okay. So how should the conceptual designs of turbo machinery components be evaluated?
Yeah, basically this is what I have shown here today, right? You make a conceptual design and run then a full high fidelity 3D CFD simulation. And at CF Turbo, we really think that these loss model based approaches and these through flow methods, these simplified methods, are really not helpful because they give you the wrong answer. Yeah, it could be sometimes right, it could be completely wrong, and this is not a matter where we want to live with. So we have enough experience now with 3D CFD, and this can be automated, and it will go faster and faster. So we think it's the right way to run 3D CFD to evaluate a conceptual design always.
Okay, so from using other ways, you said that it gives you the wrong answer. Can you go into that a little bit more?
Yeah, the thing is these, I call it simplified method, right? Loss model based approaches or through flow. You don't cover the physics accurately, right? And many flow phenomena in a turbo machine, yeah, flow separations and such things cannot be covered with a let's say frictionless method, for example, or with loss models which are based on some empirical data, right? And so that's why the prediction for the design it's fine, but for a prediction of a performance, I would not do, and that's why we choose the way we want to go with 3D CFD. We want to get reliable answers for our designs. This is the way in the end. Yeah.
Absolutely. And I have to agree that, you want to have as much information as you can and knowing that it's actually going to work when you're in that design stage and not have to just go back to the drawing board. So what's special in CF Turbo compared to other conceptual design codes?
I'll take this one. What sets CF Turbo apart is that it's a user-friendly system, not only for experts, but also for beginners. It allows you to create detailed 3D modeling. The user instantly gets a reasonable, efficient turbo machinery design proposal. And we also have excellent interfaces for all significant CFD codes, including workflow setups.
Awesome. So for workflow setups, can you tell us more about design and simulation workflows?
Yeah, well, as mentioned before, we have interfaces to all major simulation codes, and we easily can put CF Turbo in optimization workflows with commercial optimization software. And that's actually what we will be covering more of in our next webinar.
Awesome. So what is next for CF Turbo?
Right now, we're working on continuously improving the software with 2 major releases every year. And new features are based on customer requirements and requests. They will include, for example, an enhanced reversed engineering method to import legacy designs. And this year specifically, there will be an all-new CF Turbo module for axial compressor design. And finally, we are developing an impressive workflow manager for automated design and simulation that will be released soon as well.
Very exciting stuff. I'm excited to be able to learn more about that later on in the year once you are able to officially launch those new things. So thank you, Chelsea. Thank you, Ralph. This has been a great webinar. And for everyone that is watching this, you definitely need to make sure to keep an eye out for part 2 of hydraulic designs of multi-stage pumps. And for part 2, it'll be all about optimization. So if you're watching this, we will make sure to send you the part 2 whenever it's ready. And if not, then we will we'll have it up on the website for you at a later date and keep you posted.
Thank you, Becca.
Thanks, Becca.
Thank you.